So we know that the ideal gas has an equation of state that goes PV is nRT. But what about non-ideal gases? Well, this is one example of an ideal gas equation of state. It's called the vanderWaals equation. So how we're going to make a couple of modifications to the ideal gas equation. So first of all, we allow that the molecules have some size, and that's going to reduce the free volume available for particles to move around. So where we had V before, we're going to replace that with a little bit less volume available for particles to move around. So we're going to use B as a sort of a constant representing the meters cubed per mole. That's the molar volume of the atoms themselves, and then we multiply by n and say, okay, that's the space that's not available for the gas particles to move around. So we'll take volume and replace it with this. So where we had PV as nRT, we now have P, V minus NB is nRT. And that's the first step in the vanderWaals equation. Now the next step involves looking at pressure. So let's rearrange this and solve it for pressure. And now think about how pressure is going to be different if we allow for non-ideal gas behavior. And the behavior that we're going to be interested in is the attraction that non-ideal gas particles have on each other. Now there's a weak attraction between the molecules. So what's that going to do? Well, it's going to slow down particles that are about to collide with the walls of the container. Now, slower particles means less collision force when they collide with the container wall, means less pressure, because it's all of those little molecular collisions added together divided by the area that equals the pressure. Okay, so the interaction is going to reduce the pressure, but by what factor? How can we model that? Well, the attraction due to the non-ideal gas behavior is going to be proportional to how close those particles are together, i.e. to the density, number of moles over volume. So that's the factor that's going to slow down each given particle. However, the number of particles being slowed down is also given by that same term. And consequently, we expect a pressure reduction that looks something like this. This would be the force on any given particle. This is the number of particles that are experiencing it. And then there'll be some sort of interaction strength that measures how attractive these two particles are. So this will be large if there's lots of intermolecular forces and small if it's not. So it's the interaction energy per unit molar density squared. Has the wonderful units of pascals, and then this is meters cubed over moles all squared. So we expect the pressure to be reduced by a term of this form. So where we had P, we're going to expect something like P minus A n squared over B squared. So if we put that into our equation from above, which was P was nRT over V minus NB, we're now going to reduce that by minus A n squared over V squared. And I'm going to bring this over to join pressure and put it in a bracket, and then I'm going to cross multiply that back up. And in so doing, I'm going to arrive at the vanderWaals equation, which has this form. So it is P plus n squared A over V squared. So that's actually a pressure reduction term due to the interaction. V minus NB, that's saying there's less volume available due to the finite size of the molecules, equals nRT. This is the vanderWaals equation of state, and A and B are the vanderWaals constants. B measures the size, A measures the strength of the intermolecular force. And there are tables of these constants for various gases, so these are a couple of values for helium gas. We'd like to convert these to SI units. So this is 0.0346, and the units are liters squared atmosphere per. So liter squared atmosphere per mole squared. So first of all, we have to convert liter. So a cubic meter is 1,000 liters, and then we have to do that twice. Then we have to convert atmosphere. And so 101,325 pascals is atmospheric pressure, is 1 atmosphere. So this is the A constant. And if you work this out, it ends up being 3.50 times 10 to the minus 3. And the units are Pascal meter 6 per mole squared. What about the B constant? Well, here it was given as 0.0237 liters of volume per mole. A cubic meter is 1,000 liters, so I get 2.37 times 10 to the power negative 5 meters cubed per mole is my B constant. So the van der Waals equation of state for helium then is going to be pressure plus n's the number of moles, just like it was before. V is the volume that the gas has to move around in, just like before. And then we have this constant here. It's 0.00350. That's the A constant. I won't put the units in. Then we've got V minus n the number of moles times 2.37 times 10 to the power negative 5, that's the B constant, equals nRT. And that will be the equation of state for helium. Now what do the isotherms look like for that? And for the van der Waals gas, we know that the ideal gas, they look like hyperbolas. Pressure and volume are just inversely proportional. And if you plot that function, so this is pressure and this is volume, so if we rearrange and solve for pressure again, we'll get nRT over V minus NB, and then we're going to have that pressure reduction, which is n squared over V squared times A, you know, something like roughly 1 over V minus a constant minus some other constant over V squared. Now you see that there's going to be an asymptote here at NB, and so that's what's happening there. Right? That's just the volume that all the gas molecules would occupy. At this point, there's no room for the gas molecules to move around, so the pressure diverges. That makes sense. And then we see that it's dropping off, and it looks an awful lot like a hyperbola. It looks a lot like an ideal gas. However, if you're careful, and if you put in the right values for temperature here, right? I kind of dropped out that detail. Something actually really interesting happens. You actually get isotherms that exhibit sort of a strange behavior here. And those look an awful lot like what we see around a phase change. So if we look at the the PVT surface for water, right, we see that as we were climbing along an isotherm, we'd reach a certain point and then we'd undergo a phase change, and the pressure and temperature would remain constant. And then once again, once we had changed phase, then we would again get a sort of a hyperbolic-like function. So there's something going on right here that looks a lot like what we've got with our van der Waals gas. All right, now that's only going to happen at a certain key range of temperatures. Well, that makes sense because we only see that behavior happening on a certain part of the phase plane. So the ideal gas, again, it would be PV is nRT, or P is nRT over V. So if they're isotherms and the temperature is constant, then it's just pressure is proportional to reciprocal volume. And certainly at high enough temperatures, that's what you see on the van der Waals as well. It's just a hyperbola. But at that important temperature, in that key range, you start to see these sort of cubic-like functions happening. And what was suggested is, what we're really seeing there is that phase change, that dome shape. And then right here is just where we're starting to see, we're starting to get into a mixed phase region. And here, with these little curves, what was done is, this is known as the Maxwell construction, is saying that this obviously isn't physical, right? Because the pressure is not going to decrease and then increase again. So what was done here is known as the Maxwell construction. It was just drawing a straight line across there and saying, okay, this really doesn't happen. There isn't an oscillation in pressure there. So what really happens is the pressure just drops along that isotherm, remains constant for a bit while the phase is changing, and then drops again on the other side. So if you add that Maxwell construction to these van der Waals isotherms, you get something that looks a lot like a phase change. And that, of course, is interesting because ideal gases don't exhibit a phase change. So this is non-ideal gas behavior that we're getting from a fairly simple modification to our equation. Okay, so we're excited about that because we made a couple of small changes. We modified the volume a bit, we modified the pressure term a bit, and now we've got something where you can say, hey, you know, we're kind of modeling what's going on in phase change here. Now, when we meet in class, we're going to derive an expression for this point right here, which is the critical point, rewrite the van der Waals equation in terms of that critical point, and then I'll show you how to zero in on this interesting range here so we can actually plot these isotherms. But that's it for our pre-lecture for today. This is an introduction to the van der Waals equation of state, which is a non-ideal gas equation of state.